Hello friends, today's topic of discussion is binary search tree. Binary search tree is a special binary tree in which the data is sorted in an order so as the value in the root node will be more than that of the values of the left subtree of the root node and which will be less than that of the value of the right subtree. So, all the left subtree nodes will have less values than the value of the root node, and all of the right subtree nodes will contain greater values than the root node value. So, suppose if I write the binary search tree, the definition of the binary search tree in a recursive way, I can write it is binary search tree is a binary tree which is either binary search tree is a binary tree which is either empty, which is either empty or in which the following criteria hold. Number one criterion is all keys of the left subtree of the root are less than the key of the root. Number two is similarly all keys of the right subtree of the root are more than the key of the root. And number three, the left and right subtrees, the left and right subtrees of a binary search tree are binary search trees once again. So, these are the three criteria which will hold in case of a binary search tree. So, binary search tree is nothing but a binary tree which can be an empty binary tree or which can contain the have the following criteria. So, what are the criteria? Number one criterion is all keys of the left subtree of the root are less than the key of the root. What is the key? Key means the value contained in the node, and all keys of the right subtree of the root are more than the key of the root, that is greater than the key value of the root, and left and right subtrees of a binary search tree are as well binary search trees themselves. So, this is the definition of a binary search tree. So, let me just draw a pictorial representation in order to make this entire concept clear to you. So, let me draw a binary search tree on the board to explain you how it works. Suppose I am just wiping a little bit of portion from the bottom in order to draw the binary search tree. Suppose I am drawing one tree like this. Suppose I have drawn like this. So, this is a binary tree. And what are the contents? Let me write the contents in a way so as the conditions of the binary search tree holds and the conditions are applicable on this binary tree which I am drawing. Suppose let me write here 20. Suppose I am writing here 18. Suppose I am writing here 16. I am writing here 18. I am writing here, say suppose 12. I am writing here 14. Let me write here 32. I am writing here 28. Writing here 25. I am writing here 38. So I have written some values on this binary tree's nodes, and let us analyze what I have written. Suppose I have written 20 over here. So this is the root node of the entire binary tree. This entire left subtree contains values. See this 16, 12, 18, 14. All the values are less than the key value of the root node. So this is one of the conditions of the binary search tree which is now holding good. And on the right subtree, we see all the values 32, 28, 38, 25, all are values which are greater than the value 20. So, in this way, we can say that as far as this root node is concerned, the left subtree and right subtree are subdivided or partitioned in a manner so as to contain less values on the left side and more values on the greater values on the right side. So, this apparently looks like a binary search tree. Let me just see whether the recursive approach follows for every node of the binary search tree, because every node should be considered as a root node, and on that very node we have to consider it as the root node and see on the left subtree of that root node if the condition of the binary search tree holds, and on the right subtree of that particular node we will see, we'll try and find out whether the values are greater on the right subtree. So that condition should follow for every node of the binary tree in order to make the binary tree a perfect binary search tree. So suppose let me move on to this node 16 containing the value 16. So if we can consider this to be the root node of this tree, this portion. So in this case we see the left part contains 12 which is less than 16, okay, and we go to the right of that 12 and see that 12 has a value which is the right subtree has a value 14 which is greater than 12. So everything is okay till now, and let me analyze the entire left subtree of this 16. Left subtree of 16 contains value 12 and 14, both of which are less than that of 16. So everything is good up till now. We go to the right subtree of 16 and see right contains 18 which is greater than 16. So everything is good up till now. We will now move on to this 32 and analyze the left subtree of 32. See, this left subtree of 32 contains 28 and 25. All are less than 32. So it's good. And 38 on the right subtree, that is more than 32. So it is also maintaining the condition of the binary search tree. Suppose we go to this 28 and see there is a left subtree part of 28 which is represented by the node 25, and 25 is definitely less than 28. So we see that every node of this tree maintains the condition which we have described in the explanation in the definition part. So what we have drawn over here is nothing but a perfect binary search tree in which all the conditions of the binary search tree holds. Let me draw a binary search tree in a way to contain some character data and see how it works over there. Suppose I am drawing a small binary search tree like this. Suppose like this. I am writing over here M. I will write over here D. I will write over here G. I will write over here R. I will write over here P. Suppose this, see this, try to analyze this tree. This is a binary tree, and see this M. If this M is the root node, then we go to the left subtree and see whatever is on the left subtree of M are, according to dictionary, comes before M. Let us see D and G. Both of these comes before M in the alphabetical order or in the order of the dictionary. And on the right subtree we see that these values, that is R, this characters R and P are all characters or letters of the English alphabet which follows the letter M. So in this way we can see the left subtree is something which is coming in the dictionary order before the M, and on the right subtree something which is coming after the M in the dictionary order, that is in the lexicographical order. And for individual trees, let me see this left subtree of M. Suppose the root node of this left subtree of M contains D, and there is no left subtree of this D, there is a right subtree, and let me see G. G comes after D in the dictionary order, that is in the lexicographical order. And in this G, there is no child, so we need not test that. We can see this R. R contains a left subtree in P, and P comes before R in the lexicographical order, that is P, Q, R. So R comes after P in the dictionary order. So in this small binary tree which we have drawn, we see that everything follows the dictionary order or the lexicographical order. So this can be also called a binary search tree in this sense, that all the data are partitioned in a manner so as to represent the dictionary order or the lexicographical order. In this way, this can also be considered to be a binary search tree, and this special binary search tree is called a lexicographical tree. So a lexicographical tree is also a binary search tree. So this is the brief overview of a binary search tree, and there is one thing which needs a bit of explanation, that is the structure definition of each of the node of the binary search tree, but that is quite similar to that of the structure definition of a normal binary tree like this. If we just go on to write the structure definition, I will just write like this: type def struct node. I'll write suppose cat data or int data, like I am writing char data, and I will write struct node star left star right. The writing is encroaching on the figure, please bear with that. And now I will write like this: BS node, that means binary search tree node. So what we see over here, char data is the character part, and struct node star left and star right means the pointer to the left child and pointer to the left subtree and pointer to the right subtree, and this BS node is the type defined in this structure declaration. So suppose this 20, if we take this 20 to be an example and depict it by means of this structure, the node will contain like this. The node will contain a value, not this 20 because I have written cat data. Let me just consider it to be the M node, this one. I will write M over here, and there will be a left pointer and there will be a right pointer. Suppose this has an address of 606, this has an address of 505, this is an address of 707. So this M will contain a value of an address. The M will have an address of 606, and its left pointer will point to 505, and its right pointer will contain the value 707. So this is one node, one representative node of this binary search tree for the node containing the data M. So if you have any doubts and queries pertaining to this entire explanation, a brief overview of the binary search tree which I have given you, you can well post your doubts and queries into the comment section below so that I can address them. Thanks for watching this video.